Hello, everybody, and welcome back to another Teach Astronomy stream. Hope everybody's doing well on this Monday morning. My name is Victoria, if you haven't been here before, but you can call me Vicky. And I see we've already got some people talking in the chat. How are you guys doing? Hope your beginning of your week is going well. I see everyone's from the eastern side of the U.S. that's talking. So far, the East Coast is dominating the West Coast. I would agree, have to say. So today, like our regular Monday streams, we're going to be doing a book stream. We're going to be reading Einstein's Monsters. Last week we did the first half of chapter 7 because chapter 7 is a little bit longer than the other one. So we're going to do the second half today. So it probably won't be the usual 2-hour stream. It'll probably be closer to an hour. Also, hello from is KY Kentucky, I think. Hello from Kentucky. I'm hoping it's Kentucky. Hope you're doing all right. But yeah, so we're going to be continuing the chapter Seeing with Gravity Eyes that we started last time. So very exciting. And yeah, we're just going to be hanging out, having a good time. Glad you all could make it. I hope everyone's doing well. And yeah, I know we couldn't hang out on Friday because we didn't have our normal amateur astronomy, but that's going to be coming back not this week, but the week after because there was a grant due, and then this week is AAS online. It's the astronomy convention, so or conference is the more official term. But that won't, so that will be occupying Matthew a little bit. So, you got book stream and you got news chat this week, and we will start book stream now. Okay, so we left off last time. If you are following along, we left off on page 204. If you have a hard copy of the book or a PDF. In the section, right before the section, Meet the Maestro of Gravity. So I will start there. The world's preeminent gravity theorist originally wanted to be a snowplow driver. Kip Thorne was at home with snowstorms and mountains as a child. Growing up in the Rocky Mountains, that's the most glorious job you can imagine. But then my mother took me to a lecture about the solar system, and I was hooked. He was raised Mormon in a conservative area of Utah, but is now an atheist. His parents were both academics, so they encouraged his curiosity. Thorne's career moved swiftly. After earning degrees at Caltech and Princeton, he returned to Caltech, where he was one of the youngest people ever to be made a full professor. He'd left Utah as a gaunt and geeky Mormon, his shyness hidden behind a messianic beard. By age 30, he was a world expert on gravitational astrophysics who favored jeans, a black leather jacket, and a hipster goatee. Thorne did his PhD thesis under John Wheeler at Princeton. Wheeler posed an intriguing question. Would a cylindrical bundle of magnetic field lines implode under its own gravitational force? Magnetic field lines repel one another, and after difficult calculations, Thorne proved it was impossible for a cylindrical magnetic field to implode. This led to another question. Why then are spherical stars, which are also threaded by magnetic field lines, able to implode and become black holes? Thorne figured out that gravity can only overcome interior pressure when it acts in all directions. Imagine a hoop that can be spun to trace a sphere. Any object of mass m around which a hoop with circumference 4 pi gm divided by c squared can be spun must be a black hole, where g is the gravitational constant and c is the speed of light. This was called the Hoop conjecture, and it made Thorne a superstar when he was barely out of graduate school. By the time he was in his mid-30s, Thorne had co-authored his landmark textbook, Gravitation, and embarked on his series of bets with Stephen Hawking. As a co-founder of LIGO, Thorne was deeply invested in discovering gravitational waves. He knew that the merger of two black holes would give the strongest signature of gravitational waves. But there was a problem. The only way to calculate the strongest part of the signal, just before the merger, was by using computation, since, as is the case for many situations in general relativity, the equations could not be solved exactly. However, supercomputer simulations at the time were woefully inadequate. This is all in quotes from, I believe, Kip Thorne. It was very much on our minds that those computer simulations needed to be in hand by the time we made... Oh, sorry. Let me start that over. It was very much on our minds that those computer simulations needed to be in hand by the time we might begin to see gravitational waves with LIGO. But in the 1990s, there were huge problems in the field. These great computational scientists could collide two black holes head-on, but when they tried to have the black holes go into orbit around each other, as should happen in nature, they couldn't even get them to go around once before the computers crashed. By 2001, I got alarmed, because I expected that advanced LIGO would be operational in the early 2010s, a decade into the future. It was not at all clear that the simulations would be in hand by then. End quote. So he withdrew from the day-to-day operations of the project to start a numerical relativity group at Caltech and Cornell. Thorne has a light touch as a popularizer of science. He's able to explain esoteric ideas in everyday language. As the public face of LIGO, he was able to persuade career politicians with no science background to fork over nearly $1 billion to build two huge machines to detect hypothetical, invisible waves so weak they can only shift atoms by a tiny fraction of their size. His proximity to Hollywood means Thorne has been roped into projects where gravity is a major actor. In the early 1980s, Carl Sagan set him up on a blind date with producer Linda Obst and tapped his expertise to map out the wormhole travel scene in Contact. Obst then sought him out when she was developing Interstellar with director Christopher Nolan. The movie uses a gigantic spinning black hole called Gargantua to slow down time, and Thorne worked with the animators to ensure that the visuals were scientifically accurate. Some frame took 100 hours to render, and the data for the film pushed close to 1 million gigabytes. That's nuts. I'm sorry. Some commentary from me in there. That's insane. Thorne even made a scientific discovery from the simulations that will lead to several papers. From his perspective, the images are beautiful, but he thinks they're also beautiful because they're true. And we have a figure as well. I'm going to show that to you guys. That's the end of the section, by the way. And this is the figure. It is an artist representation of the supermassive black hole called Gargantua in the 2014 film Interstellar. The true distortions of the accretion disk seen from this close would be even greater than in the image. In the film, the black hole holds the key for an astronaut to travel through time and space and save the people of Earth. Miller's planet is near the top left. It's an ocean world so close to the black hole that time slows dramatically. So yeah. Fun, cool stuff about some fun movies you guys might have seen. Oh, and Student McLeod found us a picture of Kip Thorne. Amazing, thank you. Let me show you guys that. Let's make sure I have the right thing selected. There we go. There he is. There's Kip Thorne. In front of some gravity waves. That's cool. I like that. Very nice. How is the weather in Kentucky? How's the weather for everyone? I'm so curious. I know, the weather never changes for me. It's always usually kind of sunny and kind of warm. And the coldest it gets is like 50 degrees. 50 degrees Fahrenheit, by the way. Oh, and you have a better picture of Thorne's black hole from Interstellar? Let's see that. Oh my gosh, this is a huge picture. It's probably a still from the movie. It's really nice though. So that's the planet they were talking about. If you've seen Interstellar, there's a scene where I'll try not to give anything away, but there's a scene where they go to this planet, right? They're trying to find these astronauts that were sent to other planets to like see if life and like humans could survive there and they could like colonize them. And one of the planets is this one, and it's like right next to the black hole. And so they're on the planet for like maybe 10 minutes or something, but it turns out it was like years and years because of how close it was to the black hole and like how time was distorted. So apparently, Kip Thorne helped guide the production on how to do the animations for that and the CGI for that, and how all those like how it could actually work in real life. So that's pretty cool. So the sun's trying to come out in New Jersey. Yeah. It's usually very gray there. I said it's cold in Kentucky. Now you won't go see the movie. It's a good movie. I didn't give away too much. That's like the premise. That's like the first 10 minutes where they were like, I'm going to go. We need people to go and find out if they're still alive. It is a really good soundtrack. Yeah, that and oh my gosh, what was the other one? The one about the Enigma code breaker with Benedict Cumberbatch. Oh my gosh, what's it called? The Imitation Game. That both of those soundtracks got me through like freshman and sophomore year of college, because I would just put those on while I was studying. They're very good. Very good soundtracks to work by. But yeah, it's a good movie. It's existentially a lot. So I only watched it the one time, but it's very good. It will leave a lasting impression with you. That, Contact, The Martian, those are all like very really good movies that some pretty well-known astronomers and astrophysicists like consulted on, or that or like The Martian, I guess, was like the book that it was based on was he did a lot of research to make sure everything was accurate. So yeah, fun sci-fis that are correct. Anyway, we will continue. So the next section is called Viewing the Universe with Gravity Eyes. Almost every day, a space-time ripple passes through your body due to a binary black hole cataclysm somewhere in the universe. It might approach from above, or the side, or from below your feet. You go about your business unaware of the intrusion. As the wave sweeps through, you get a tiny bit taller and thinner for an instant, then a tiny bit shorter and fatter, and the pattern repeats. After a few tenths of a second, you're normal again. It brings to mind the reaction of the novelist and poet John Updike to a different ghostly messenger of the cosmos, the neutrino. And this is a little poem. The earth is just a silly ball, to them through which they simply pass, like dustmaids down a drafty hall, or photons through a sheet of glass. They snub the most exquisite gas, ignore the most substantial wall, cold shoulder steel and sounding brass, insult the stallion in his stall, and scorning barriers of class, infiltrate you and me, like tall and painless guillotines they fall, down through our heads into the grass. That's the end of the poem. It's very nice. There are 3 types of gravitational waves. One is stochastic, I believe is how it's pronounced. So one is stochastic, a word that describes any physical process that has a random quality. This is the hardest type to detect, since the signal competes with random noise from electronics at high frequency and with geological activity at low frequency. The most exciting form of stochastic signal would be from the Big Bang, as we'll see shortly. The second is periodic, referring to gravitational waves whose frequency is nearly constant for a long time. The most common sources of periodic signals are neutron stars and black holes in orbit around each other. Since these binaries have wide separations, the signals are weak. The third is impulsive, meaning gravitational waves that come in short bursts. Bursts come from the formation of a black hole in a supernova explosion, and from the merger of neutron stars or black holes. They're expected to be the strongest sources of gravitational waves, and they have a distinctive fingerprint, so they're also the easiest to distinguish from noise. Think of black holes colliding as a gravity bell ringing. Just as a large bell makes a lower frequency sound than a small bell, large masses colliding emit lower frequency gravitational waves than small masses colliding. Neutron stars chirp in a crescendo up to 1600 Hz. Minimum mass black holes rise up to 700 Hz. And the hefty black holes detected in the first LIGO event started at 100 Hz and ascended to about 350. There are roughly 3 times as many neutron stars as black holes. So in order of decreasing number of events but increasing signal power, we expect to see mergers of 2 neutron stars, mergers of a neutron star and a black hole, and mergers of 2 black holes. LIGO was designed to have maximum sensitivity in the frequency range of 100 to 200 Hz, where merging black holes give their strongest signals. That's a sweet spot for detection. At 1000 Hz, the sensitivity is 2 times worse because noise in the electronics rise. And at 20 Hz, the sensitivity is 10 times worse as the geological rumbling of the Earth increases. What information can we get from a space-time ripple? Let's use an analogy of water ripples. Imagine you're a cork on a large pond on a breezy day. The wind is ruffling the surface of the water, and the random pattern of waves that makes you bob up and down is a good approximation of the background noise in a gravitational wave experiment. If someone starts dropping stones into the pond every second for a few seconds, you'll feel an additional bobbing motion that's periodic. That's the chirp from 2 black holes coming together. The size of the motion depends on the size of the stone, and on the distance from the place where the stone is being dropped, since ripples get weaker as they travel outward. As a cork, you have no eyes and ears, so all you feel is the motion. You have no idea where the waves are coming from. But if you could talk to a second cork nearby, you'd have more information. The ripples travel in concentric circles, so timing receipt of the 2 signals gives you the direction of the source by triangulation. That's the way your ears work to figure out the direction a sound is coming from. From detection with LIGO, physicists can learn several important pieces of information. The pattern of changing frequency gives the masses of the 2 black holes by comparison with a simulation. The merging phase is used to measure the spin of the post-merger black hole. Position of the event on the sky is measured during the time delay between the signal arriving and the 2 detectors, and the fact that a singular signal is seen at both locations help to rule out noise or a spurious signal. Oh, gosh. Sometimes these sentences are just really long. And then you got the parentheses stuff, and then it's a lot. So I'm going to start that sentence over. Position of the event on the sky is measured using the time delay between the signal arriving at the 2 detectors. And the fact that a similar signal is seen at both locations helps to rule out noise or a spurious source for the signal. With only 2 sites, the sky position isn't very tightly constrained. It could be anywhere in a broad swath. However, LIGO's success has energized the international community. Europe has just commissioned an interferometer in Italy, Virgo, and one in Germany is not far behind, GEO 600. An interferometer in Japan will go online in 2019, and another one is planned for India in the early 2020s. Detection at 3 or more sites might allow the sources of the gravitational waves to be pinpointed to a particular astronomical source and so be observed across the electromagnetic spectrum. I'm just going to take a quick break. Get some water. Everybody's talking about Interstellar before. That's a good one. I'm trying to think of other fun space movies. I've been watching the Star Wars prequels. Those are very different kinds of space movies. I had never seen them. I've only seen the original trilogy and then the first 2 new ones, because I still haven't seen the very last one. because I've heard it's not great. I've seen Rogue One too. Rogue One is excellent. I don't know if anyone's super into Star Wars here. Are you guys Star Wars fans, Star Trek fans, or neither? I'd like to know. Or I guess like Spaceballs fans. There's that too. Okay. The distance of the source is estimated by the strength of the signal. The waves move away from the black hole in 3 dimensions and are diluted as they spread through space. Gravitational waves have one great advantage over electromagnetic waves. Their amplitude is inversely proportional to distance. If black holes are 10 times farther away, the signal is 10 times weaker. But astronomers can't measure the amplitude of an electromagnetic wave. They measure the intensity, which is the square of the amplitude. And if a star is 10 times farther away, the light intensity is 100 times weaker. That's why LIGO, reading gravitational waves, has enormous reach and is able to detect cataclysms billions of light years away. What if LIGO's detection was a fluke? You can't do statistics with one event. Was the universe going to reveal its secrets in a single short song? Physicists were elated, but they were also anxious. They took solace in Einstein's words from a brief time in 1921, when it appeared that general relativity had been disproven by experiment. Quote, God is subtle, but he is not malicious. There was excitement tinged with relief when the LIGO team announced the detection of a second event on December 26, 2015. The signal was weaker because the source was slightly farther away, at a distance of 1.5 billion light years, and because the black holes were smaller, 9 and 14 times the mass of the Sun, as opposed to 29 and 36 times with the first event. An intervening event on October 12, 2015, was placed in the status of candidate rather than counted as a secure detection. It was weak because the black holes involved, 13 and 23 times the mass of the Sun, had merged not long after life began on Earth, at the prodigious distance of 3.3 billion light years. In 2017, LIGO made 3 more detections. With 5 firm detections and a 6th one on the bubble, 1,000 scientists were jubilant. LIGO was a roaring success. It is the dawn of the age of gravitational wave astronomy. And I have a figure to show you. Let's see it. So this is... There it is. This is the other detections that LIGO has made. So the first detection was on September 14th, 2015. And then there were 2 more detections in 2015 and then 3 in 2017. And the second detection that has the dashes instead of like a solid line on the circles, that one is the one that's considered only a candidate because of its signal to noise ratio being below the threshold. So those are the different solar masses and the different objects that were detected with the gravity wave detections. So yeah, very cool. Let's see. So, in August 2017, LIGO detected another pulse of gravitational waves. However, this event differed in 2 ways from the earlier detections. The signal was weaker, and it came from a source only 130 million light years away. That meant it was due to the merger of less massive objects, neutron stars instead of black holes. LIGO worked alongside the European Virgo Interferometer, and the signals from 3 different detectors enabled the scientists to pinpoint the gravitational waves with unprecedented accuracy. The neutron stars had collided in a galaxy called NGC 4993. The world's observatories swung into action. The result was a bonanza of data and the birth of a new type of astronomy. 2 NASA satellites detected a burst of gamma rays from the merging neutron stars, and over 70 telescopes across the globe caught the fading optical and infrared glow of the collision. Unlike black hole mergers, which produce no electromagnetic radiation, Neutron stars combine in an explosion 1,000 times more powerful than a supernova. One result was the burst of radiation, and another was a flood of neutrons that powered a cloud of radioactive waste. Within a day, the cloud expanded from the size of a city to the size of the solar system. Neutrons impregnated atomic nuclei and built them into heavier elements. Theorists estimated that the event created 200 Earth masses of gold, worth about $10 to the $31 if you could bring it home. That's insane. The combination of gravitational waves and a rich harvest of electromagnetic information has been dubbed multi-messenger astronomy. It's expected that LIGO and Virgo will see about one neutron star merger every week, along with one black hole merger every 2 weeks. The cosmos is awash with space-time ripples, and finally, astronomers have eyes that can see them. Accolades have followed swiftly. There's often a long time between a discovery and the subsequent award of a Nobel Prize. In fact, some eminent scientists have died waiting, and the prize cannot be awarded posthumously. But there was little doubt that detecting gravitational waves would be quickly recognized. Therefore, it was not a surprise when in October 2017, less than 2 years after LIGO felt its first shimmers in space-time, Rainer Wess, Kip Thorne, and Barry Barish were named the winners of the Nobel Prize in Physics. And that's the end of that section. Oh gosh. What is this? That Student McLeod just sent. So he said that this is an interstellar pic, which it is, with Matthew McConaughey in the foreground and me off near the ship. I don't know if I'd want to go there. That's the planet where you lose like a decade of your life in 5 minutes. But yeah, it's me. It's true. Right there. That's me. Mm-hmm. Pratik, you finally got the stream first time. Well, welcome. Thanks for hanging out. Sorry that we have I know sometimes since all of our streams are kind of at similar times, it's tough to catch one. You want me to sign your Interstellar poster? Oh, for sure. Oh my god. But yeah, we're glad you're here, Pratik. Welcome. All right. So, next section is collisions and mergers of massive black holes. Now that space-time ripples have been detected, here's what we can expect. There are 1 billion neutron stars and 300 million black holes in the Milky Way. Plenty of candidates for mergers. However, the odds of them being in close binary systems are very low. So the black hole merger rate is about once every 500,000 years. That sounds like a lot of waiting around. But the sensitivity of LIGO gives it enormous reach across the universe. When advanced LIGO is back online in 2020, well, we're done with 2020 now, I guess. So I guess it came back online last year. Its sensitivity will be 3 times greater, which means that it can detect the same signal 3 times farther away. It will measure displacement to an incredible level of 1 part in 10 to the 22nd. Since volume is proportional to the cube of the distance, the number of targets will go up by a factor of 30. The event rate could be as high as 1,000 per year, or a couple every day. The next regime will be to study gravitational waves emitted when the supermassive black hole at the center of a galaxy swallows a compact object, like a neutron star or a black hole. To return to our sound analogy, the more massive the black holes, the longer the orbital time as they merge and the lower the frequency of the characteristic chirp. The supermassive object creates sounds in a frequency range of 10 to the negative 4 hertz to 1 hertz, and an orbital time of hours to seconds. Signals from a supermassive black hole would be below the range of human hearing, even below the lowest organ pipe. Sounds more felt than heard. Because their frequency range is so low, A detector must be located in the pristine environment of space in order to register gravitational waves from the most massive black holes. The proposed tool for the job is LISA, the Laser Interferometer Space Antenna. LISA will be a constellation of 3 satellites arranged in an equilateral triangle with separations of 1,000,000 kilometers. This configuration is 10 times the size of the moon's orbit, and it will orbit the sun at the same distance as the Earth, but trailing the Earth by 20 degrees. One satellite is the master, with the laser and detector, and the other 2 are slaves. Oh, don't like that. With reflectors attached to test masses made of an alloy of gold and platinum. LISA is designed to measure displacements smaller than the size of an atom over a distance of 1,000,000 kilometers, or a precision of 1 part in 10 to the 21st. To detect tiny space-time ripples, the test masses must be immunized. The test masses must be immunized from any force other than gravity, as if they're not part of a spacecraft and are simply in the free fall of their Earth-Sun orbit. This engineering challenge requires exquisite control of the spacecraft. Each spacecraft has to float around its test mass, using capacitive sensors to determine its position relative to the mass, and precise thrusters to stay perfectly centered on that mass. In 2016, a test mission from the European Space Agency called LISA Pathfinder successfully demonstrated this technology. The success of LIGO led to a funding commitment in 2017, and the prospects for LISA are bright. In the standard model of cosmology, structures are built up hierarchically by the merger of small objects and accretion of surrounding matter. So dwarf galaxies combine to form large galaxies, and large galaxies keep growing by combining with more abundant dwarf galaxies and by gas falling in from the intergalactic medium. The central black holes follow a similar buildup process, but details are difficult to predict because they depend on a complex accretion process and the particular conditions in the centers of galaxies. Just going to take a quick pause. Oh, you have a picture of Lisa? Excellent. Yeah, we were talking a little bit about Interstellar before, because this chapter was talking about Kip Thorne, and apparently he was their kind of like science expert on set for that project, or maybe not on set, but in production. So this is Lisa. Oh, thank you so much for the cheer. You're an anonymous cheerer. Oh my gosh, that's so cute. They're a little ghost. Wow, well, thank you for that. That's adorable. I've never seen that before. Thank you so much. But yeah, like I was saying, this is Lisa. This is Lisa. So this is it's a artist rendering of that plan for it looks like one of the satellites that will be part of the trio of Lisa satellites. Oh my gosh, what is this? Oh my god. As Student McLeod said, the machine I used to visit my dad at the beach. This is from the movie Contact. If you haven't seen Contact, it will make probably 0 sense to you, but you should watch it. It's very good. I'm not going to give away anything about that one, besides the fact that part of it takes place at the VLA, and it's half the reason why I'm obsessed with the VLA. The other half the reason is because it's cool. But you should watch the movie. It's very good. All right. Let us continue. All right. Mergers between supermassive black holes take place on even longer timescales and emit correspondingly lower frequency gravitational waves. A rough calculation suggests that if a pair of million solar mass black holes merged, they would emit gravitational waves with a frequency of 10 to the negative 3 Hertz and a timescale of an hour, while a merging pair of billion solar mass black holes would emit gravitational waves with a frequency of 10 to the negative 9 Hertz and a timescale of dozens of years. Catching a wave that takes years to pass through the detector requires extraordinary stability. Detailed computer simulations suggest that LISA will detect a few mergers per year. Typically situations where both black holes are in the range 10 to the 6 to 10 to the 7 times the mass of the sun. This sampling range will give us perspective on the early phase of black hole and galaxy assembly. However, the loudest events and the most spectacular mergers of black holes 1 billion times the mass of the sun happen at frequencies so low they're beyond LISA's reach. To find these gravitational waves, an array 1 million kilometers across isn't large enough. An instrument on the scale of a galaxy is required. Enter the pulsar timing array. Pulsars are dead, collapsed stars made of pure neutrons. Hot spots on their surfaces sweep across radio telescopes as they spin, and the radio pulses keep perfect time. Pulsars that spin hundreds of times a second are the most accurate clocks in the universe. Billions of light years away, 2 supermassive black holes do a leisurely dance that lasts millions of years. When they finally fall into each other's arms and merge, they bathe the universe in low-frequency gravitational waves that stretch and squeeze the fabric of space-time. Like us on Earth, the pulsars bob up and down as the waves pass by at the speed of light. The waves slightly alter the timing of the pulses. For example, a wave with a frequency of 10 to the negative 8 Hz, or 1 cycle in 4 months, might cause the pulses to arrive 10 nanoseconds early in January and 10 nanoseconds late in March. It's an extremely delicate experiment, but current radio telescopes can measure pulses with the required precision. Arrays of pulsars are used to increase the sensitivity of the experiment and give some directional sensitivity. A pulsar timing array is the most grandiose experiment scientists have ever conceived. Rather than the 4 kilometers of LIGO or the 1 million kilometers of LISA, pulsar detectors are arrayed over thousands of trillions of kilometers. The Milky Way galaxy is the detector. This is truly big science, capital B, capital S. There are 4 pulsar arrays actively looking for signals, and they are combining their data into an international array. As they add pulsars to their target list and increase their sensitivity, there's an 80% chance that one or more of these experiments will detect supermassive black hole mergers within the next decade. And that's the end of that section. And we have a figure for the end of that section as well. Oh no. I've been to the VLA. I have pictures of the VLA. Actually, my picture on this page, I think, on the about page is of me actually at the VLA. But also, as Student McLeod points out, this is also me at the VLA. Hold on, let me. That's for sure me. Uh-huh. I love it. And yeah, so let me show you guys that figure. So here we go. So this is a graph that shows the various detectors and regimes of gravitational waves compared. So to the right, at high frequency, are the sensitivity curves for interferometers like LIGO, which are sensitive to supernovae and compact neutron stars and black hole binaries merging. In the middle are did he mean at the right or the left? Sorry. Oh no, sorry. To the right at high frequency. Yes, that was correct. Okay, sorry. In the middle are space-based interferometers like LISA, which detect lower frequency events like massive black hole binaries merging. At the left are pulsar arrays, probing the lowest frequency events, such as mergers of supermassive black holes and the stochastic background from the Big Bang. So, yeah. Oh, thank you. You guys like my car. Oh, yeah. It's a good car. Honestly, I love classic cars. I don't know a lot about cars, I'll be honest, but I do love looking at them. Pratik said, better than listening to your same songs while working space knowledge. You have a space knowledge podcast? That sounds cool. Feel free to share it if you want. That sounds great. I make podcasts, but it is not anything to do with astronomy. So, yeah. But, on my About page here, I've been to the VLA. I've done it. It's happened. It's great. It's super cool. I sat on the hood of my car and got a picture. Well, it wasn't my car. It was actually the university's car. So don't tell them. But I sat on the hood of the car and I got a picture with the dishes in the background, and it was really cool. Anyway, we will continue. Gravity and the Big Bang. The wild frontier is a detection of primordial gravitational waves. Remember, ripples in spacetime are created any time mass changes its motion of configuration. By far the most dramatic changes in mass took place in the early universe, when the matter that would eventually form hundreds of billions of galaxies was contained in a region smaller than an atom. Current cosmology includes an early phase called inflation, an exponential increase in the size of the universe when it was still microscopic. Microscopic. 10 to the negative 35 seconds after the Big Bang. Inflation is invoked to explain the otherwise enigmatic flatness and smoothness of the universe. Inflation implies that the seeds of galaxies were quantum fluctuations. There's some indirect support for inflation, but the energy at that time was trillions of times higher than can be reached in the lab or in accelerators like the Large Hadron Collider, so we cannot attempt to replicate it in a terrestrial experiment. Testing inflation is important because it will bring us closer to the holy grail of a theory of quantum gravity. Gravitational waves from inflation should still be reverberating through the universe. Their energy spreads across 29 powers of 10 in frequency, encompassing all the detection methods we've discussed. However, the waves are too feeble to be measured with interferometers or pulsar timing arrays, so astronomers have focused on their imprint on the radiation that bathed the universe as it cooled enough for stable atoms to form. That radiation has traveled unaltered through the universe since 400,000 years after the Big Bang, and we observe it as microwaves. The stretching and squeezing of space is predicted to leave a slight swirling pattern in the microwave radiation. The scientific community was electrified in 2014 when a team working at the South Pole Telescope claimed to have detected gravitational waves caused by inflation. Not directly, but by inferring them from their particular imprint on radiation. The excitement was dashed a few months later when it turned out the team had been fooled by a contaminating signal from dust in the Milky Way. It was a painful experience for the researchers since they had checked the data carefully but were fooled by a subtle foreground, like having mist on your glasses and confusing it for a distant storm. The universe is a messy, complicated place that can't be controlled like lab equipment, so cosmologists are wise to be cautious. Yet, when there's competition from other groups, the urge to publish quickly is hard to resist. A number of teams are gearing up for new attempts at this important measurement. The best sites for these challenging microwave observations are near the South Pole and in the high and dry Atacama Desert in Chile. 5 teams are involved. The stakes are high. If the gravitational wave signature isn't detected, a centerpiece of cosmology will be in doubt. But if the signature is detected, it will be direct evidence for quantum gravity. A quantum origin for the universe may be a sign that we live in a multiverse, where we inhabit one out of a potentially infinite number of space-time bubbles. The universes in the multiverse are distinct space-times, probably unobservable from our space-time, which makes the idea difficult to test. They might all have the different laws of physics, and even be unrecognizably different from our universe. Do these other universes have the same fundamental forces? Do they contain black holes? Do they contain life forms that can understand their universe? These are some of the imponderable questions at the frontier of cosmology. And that is actually the end of chapter 7. That was quick. Wow. I mean, I guess we did do half of this chapter last week, so it makes sense. You're trying to figure out what car that was? I'll put it back up. When does contact take place? I don't remember. I mean, I think she has an old car for when the movie was filmed. I think that's like a thing. You think it's a Nova? Oh, hello, Charlie. How you doing? Oh, you meant my the Twitch channel. Oh, you're listening to it as if it was a podcast. Gotcha. I misunderstood. Well, I'm glad you're enjoying it. Yeah. You said you want to you work in IT, but you want to work in space astronomy? Yeah, go ahead. I mean, like, also, if you're really good at IT, there's always like ways to like, I mean, I imagine, you know, space agencies also need IT, so that's a way to like get your foot in the door and then, you know, try to shift into something else too. But yeah, I'm glad you could enjoy this. What is this? The swirling pattern in the CMB. Oh, I'm assuming the CMB is the cosmic microwave background. But this is, as Student McLeod said, it's the swirling of that cosmic microwave background. It's a pretty little chart. Yeah, Contact came out in 97, so I think, yeah, I was gonna say, I know it came out in the late 90s, but I wasn't sure if like how early the book and like the movie were supposed to take place, you know. I wasn't sure if it was like 70s or 80s, because yeah, Sagan wrote it in 85, or published it in 85. I have not read Humble Before the Void. I have it, and actually it might be it. I'm gonna put it in as one of the options for the next book that we do, because we're gonna do a poll, not right now, obviously, but I need to see how many more chapters are in this book. Are we going to be done with it next week? I guess we will find out. Oh my gosh, I think we are. Yeah, there's only one more chapter left. It's called The Fate of Black Holes. And it's about doing some math. It's less than 30 pages. It's like 25 pages. So, yeah, we'll probably finish the book next week. That's exciting. I have to contact Chris and see if he can do an author talk the week after. So hopefully he'll be able to do that. And I'm going to try to get him for the same time as usual. So next week's going to be normal. But the week after, which is the 25th of January, I'm going to try and see if I can catch him at the right time that we normally do this. I think he should be open because they finished their grant applications, and that's kind of been taking up a lot of his time. So hopefully I'll get him for that, and then we can ask him a bunch of questions. So also, if you guys have any questions that you know of now that you want to make sure I ask him, because I'll have some questions too and stuff, but feel free to start sending those in. I'll start writing them down if you send them in now or next week. But anything that has to do with like what we've been talking about specifically, so like the black hole stuff, anything you may have wanted him to like expand upon, or especially what I really wanted to talk about is like the writing of the book, the research behind the book, things like that, how he went about doing all of that. And maybe if you have any questions about like certain anecdotal stuff that he put in there, that would be cool to talk about too. But yeah, so next week we will vote, I guess, we'll finish the book and then we'll vote on what book we do next, which is very exciting. So in the meantime, how about you guys, I'll show you guys Chris's website. You can probably just type in Prof Impey and you'll find it, but we'll look at it together. Here it is. And he has all of his books here. So Humble Before the Void is, I'll give you a very quick little summaries of these. Humble Before the Void is more of a narrative, or not narrative, more of a, what's the word? memoir-ish kind of thing about his trip to do this like conference thing with Tibetan monks and the Dalai Lama, which is really cool. Very cool story. I've heard him talk about it a little bit. I haven't read the book though. Shadow World is his only fictional novel. It's a science fiction book. I think it's science fiction. It's at least fiction. And I read the first like couple chapters of that one and then couldn't keep the book. So that was unfortunate. Encountering Life in the Universe. I actually don't know too much about that one. I mean, the rest of these are regular, like similar to Einstein's Monsters. Oh, is January 25th his birthday? Okay, I guess that's not gonna work out, huh? Let me verify that, because I'm friends with him on Facebook. So I can figure that out. Yeah, that's not gonna work, huh? I don't want to make him work on his birthday. That'd be mean. Does he not have his birthday on here? Chris. Gosh. Oh, no, it is. Yeah, it's January 25th. Okay, we're going to have to figure something else out for that day then. Shoot. What should we do after that? You can make it an online party. Yeah, I mean, that's what we normally do. When we be doing the favorite astronomy website session, we're actually going to, I'm going to break your visit dad at the beach machine if I missed that. We're doing it on this Wednesday. If you can make that. I mean, we'll probably do it another time as well, but our plan is to do it this Wednesday at, where's my schedule? At 11 a.m. my time, so right about now for you guys. On Wednesday we'll be doing that. So yeah, so definitely come by to that. That'll be with me and Michael. We'll be talking about and sharing some of our favorite online resources, so like different websites and YouTube channels and podcasts and all that good stuff about astronomy, so you can do some other learning stuff, because we're here, but there's also a lot of other really great places to learn about astronomy on the online, and there's so many that we thought it would be fun to share all together. Hello, welcome new viewer. Unfortunately, we're about to wrap up, but before we do, oh yeah, and I saw someone said Life in the Universe and how it began would be great. Yeah, because Chris also has how it began and how it ends. Did he write how it ends before he wrote how it began? I'm so... I don't think he did. But for some reason it looks like he did. But yeah, so we will vote on these next time. Or maybe we vote the time after that, because it'll be Chris's birthday, so he won't be able to come on. I'll figure something out. I'll talk to him. We'll figure it out, and it'll be great. But before we wrap up today, I just wanted to do the little housekeeping stuff. So like I said, this Wednesday we have a stream at 11 a.m. Pacific time, my time, which is right now. On Wednesday, we will be doing, like I said, that chat about... Oh, you wish you could access the Impey Pereira Hardy Greelman Wenker calendar. Yeah, it's just we don't have a calendar is the problem. That's the main problem. We're trying to have a lot more consistency with stuff, because it's all over the place and it's hard. Chris's Q&As are kind of always going to be all over the place, just because his schedule is insane. Oh, thank you for the follow. What no? Thank you so much for joining the Teach Astronomy family. But yeah, Chris's sessions are always going to be kind of all over the place, just because his schedule is always all over the place, because he's doing different things like every day all the time. But we are going to be finding a consistent day and time. Well, the days are going to stay the same, but a consistent time for astronomy news chat and amateur astronomy, because we want consistency, and it helps. So once Michael goes back to classes starting this week, we will know, and that will stay the same. And then when Michael comes back, that will stay the same. Or Matthew comes back, that'll stay the same. So it'll be great. And you asked, have I ever used a VR headset for astronomy stuff? No. Okay. So I've only ever used a VR headset once ever. And I tried it playing a game. It's a game called Super Hot, and it's this first person action shooter game, but every time you everything's in bullet time. So if you don't move, time does not progress. So you can do things, and if you move, then time progresses. So you it's cool. It's weird to explain, but it's an interesting game. And I got so dizzy so fast, and I don't know if it's because it's the first time I ever did VR, or if I was not prepped, but it was crazy. But that's also because I have pretty bad motion sickness. I can't usually ride in a car unless I'm driving, or I'm in the front seat doing absolutely nothing, reading nothing, looking at nothing. I have to just look forward. So that's probably why. But I'd like to try it again. But you just got an Oculus Quest. That's awesome. That sounds really cool. Yeah, it would be really cool to watch some of those really cool artist rendering kinds of astronomy videos, or going through space or things like that through VR. That sounds really cool. But yeah, okay. So housekeeping stuff. Yeah, we will be back on Wednesday, and then I believe Thursday is, let me check it's not a schedule. It's just messages between Matthew and Michael and I. But yeah, Chris will have a stream this Thursday at 10 a.m. Tucson time, which is 9 a.m. for me. So 9 a.m. Pacific time on Thursday. We will be here for Chris's not amateur astronomy, for Chris's Q&A on astronomy and astrophysics. And I think that's it for this week. Also just a quick reminder, if you were a subscriber before and you are not a subscriber now, remember that it rolls over every month, and it's really annoying because it makes you resubscribe. So if you want to keep subscribing, just make sure to check on that. And especially if you have a Prime subscription, because it's still free to you, but it will make you resubscribe every month, because it loves to steal money from creators when people intend to subscribe. But it only lasts for a month, so you just have to make sure that redoes. And also, if you have been watching and you would like to subscribe, that would be awesome. It really helps out the channel. But if not, that's totally fine. Just make sure you follow, because that helps a lot as well. And that's pretty much it. So I guess I will see you guys on Wednesday. Have a good one, and thanks for joining. Bye. Oh, Matthew will be back on Friday. No, next Friday. Matthew will be back next Friday, the 22nd. And Amazon Prime subscriptions do help. Yes, those are awesome. And those are amazing. And thank you so much for that. I will see you all next time. Bye.